Bismillahirrahmanirrahim. Dear students, let's discuss the problem of this week. And the problem that I have designed for this week is of cantilever beam, and there are two new things that we will learn in this problem. One thing is that in this cantilever beam we have support on the right side. There is no support present on the left side. So one student asked that how to analyze such situation when we do not have any support on the right side, on the left side, but there is only one support on the right side. So I decided to study that case in this week. So we have just one support on the right side, and secondly, in this problem we have multiple loads present at a single point. You can see that we have a UDL spanning from point A to point C, and at point B there is a point load acting with magnitude of 10 kilonewton, and a couple is also acting at point B with a magnitude of 20 kilonewton meter. So this is the second new concept that we will learn in this problem. Our objective is the same. We want to draw a shear force diagram, bending moment diagram, and elastic curve of this beam. So let's see how to solve this problem. Our first step, as always, is to determine the reactions of this beam, and we have a cantilever beam, so there will be a vertical reaction at support D, and there will be a moment at the support D. Excuse me. So I have assumed the reactions at point D. RD is in upward direction and MD is in clockwise direction. To calculate the reactions, we will apply the conditions of equilibrium, sigma Fy equal to 0, with the convention that upward forces will be treated as positive. So if we start from left side, we have a UDL acting in the downward direction. So this minus 5 into 10 is the area of this UDL, minus 5 into 10, and then this minus 10 kilonewton load acting in downward direction, so minus 10, and then plus RD. RD is assumed in upward direction, and that should be equal to 0. Now in this equation we have only one unknown, so RD comes out to be 60 kilonewton. Next, for resistive movement, we will apply sigma MD equal to 0 with the convention of clockwise movement as positive. First of all, this UDL, the area of the UDL is 5 into 10, and the resultant will be acting at the centroid of the area, means here at point B, and this resultant that will be acting here in the downward direction will produce movement in counterclockwise direction about point D. That is why we have taken it as negative. So 5 into 10 is the magnitude of the load, and 15 is the lever arm, because the resultant will be acting at point B, and the distance of point B with respect to support D is 15. Then next is this 10 kilonewton force. It's also producing counterclockwise movement about point D, so with a negative sign. 10 and 15 is the lever arm of this 10 kilonewton force. Then this 20 kilonewton meter movement acting in clockwise direction, so it will be taken as positive. And the last one is MD, which is acting in clockwise direction, so it will be taken as positive, and that should be equal to 0. Now if we solve this equation, we get MD equal to 880 kilonewton meter. So in this way we have calculated both the reactions of this beam, and next step is to divide the beam into number of portions. And we know the principle. The principle is that wherever we see any change, any abrupt change in applied loading or any change in support condition, we divide the beam into two separate portions from that point. So starting from point A, we see a point load and a point movement acting at point B. So from A to B we can have one portion, then from B to C, because the UDL is ending at point C, so we will take BC as the second portion, and then CD is the third part. No load is acting at C in portion CD, but we have a support at the end, and this is the extreme end, so this portion has to end at point D. So there are three portions, AB, BC and CD. Now we will consider each portion one by one. We will draw its free body diagram and we will write down the equations for shear and bending moment. For portion AB first, the x will vary from 0 to 5 meters for portion AB, and in this region we have a UDL. Intensity of UDL is 5 kilonewton per meter and it is acting over span x. Now if we apply sigma Fy equal to 0 with the convention of upward forces as positive, then this 5 kilonewton per meter UDL is acting over span x and it's acting in downward direction, so it should be negative minus 5x, and then the exposed shear V is acting in downward direction, so minus V equal to 0. This gives us V equal to minus 5x, and at A x is equal to 0 and at B x is equal to 5 meter. If we put these values of x at point A and B, we get V equal to 0 at point A and we get V equal to minus 25 kilonewton at point B. B is equal to 0 at point A. If you look at point A is a free end and there is no concentrated load acting at the free end. So the shear should be equal to 0 at point A. Then the equation of moment. We'll take sum of moment about the section with clockwise moment as positive. So 5x is the resultant, magnitude of the resultant, and it will act at distance x by 2 from the section. So minus 5x into x by 2, and then the exposed moment m is acting in counterclockwise direction, and that's equal to 0. If we rearrange the equation, we get m is equal to minus 2.5 x square. If we plug in the values of x for point A and point B, we get MA equal to 0 and we get MB equal to minus 62.5 kilonewton meter. Point A is free end of the beam and there is no point couple acting at point A. So the magnitude of moment at point A should be equal to 0, and that is coming out to be 0. So that is fine. Now let's move to the next portion, portion BC. For portion BC, we will cut the section somewhere over here. Let me change the pointer so that it becomes more prominent. Okay. So here is the free body diagram of portion BC. We have UDL acting up to the section. At point B, there is a point force with a magnitude of 10 kilonewton and a point moment 20 kilonewton meter, and the intensity of UDL is 5 kilonewton meter. Now if we write down the equations of shear and equation of moment, let's see what do we get. X ranges for from 5 to 10 meters, and for sigma Fy equal to 0, if we take upward forces as positive, then how much is this UDL? 5 into x. So minus 5 into x is the resultant of the UDL. Then minus 10 kilonewton is acting in downward direction. And this is exposed shear V minus V, and that should be equal to 0. If we rearrange the equation, we get V is equal to minus 5x minus 10. At point B, x is 5 meters, and at point C, x is equal to 10 meter. So if we plug in these values in the equation of shear, we get VB equal to minus 35 kilonewton and VC equal to minus 60 kilonewton. So this completes the shear calculation for portion BC. Next is the moment calculation. We'll take clockwise moment as positive. If I just zoom out a little bit so that you can see the equation and the free body diagram simultaneously. Okay, first of all, this UDL resultant will act at the center. If this span is x, then UDL resultant will act at x by 2 from the section. So minus 5 into x is the magnitude of UDL, and x by 2 is the lever arm of the resultant with respect to the section. So minus 5x into x by 2 is the moment about the section due to the UDL, and then we have minus 10 into x minus 5. Minus 10 is this 10 kilonewton force which is acting at point B, and it is producing movement in counterclockwise direction about the section. That's why it's taken as negative, and x minus 5 is the lever arm. Here I have marked x minus 5. And then this 20 kilonewton meter, because it's a movement, it's a couple, it will show up in the equation of movement. So plus 20 because it is in clockwise direction, and then minus this exposed moment. That should be equal to 0. Now if we rearrange this equation, we solve it, what do we get? We get m is equal to minus 2.5 x square minus 10x plus 70. X is involved in this equation, so it means that we need to calculate the value of moment separately for point B and point C. For point B, x is equal to 5 meters, and for point C, x is equal to 10 meters. So if we plug in these values in the equation of moment for portion BC, we get mb equal to minus 42.5 kilonewton meter and we get mc equal to minus 280 kilonewton meter. Then this completes the equation, the calculation of moment for portion BC. Now let's move to portion CD. For portion CD, we will consider a section somewhere over here. So the entire UDL and point load and this couple will be present on the left side of the member, left side of the section. So here it is. We have cut the section here. The entire UDL is present, point load is present at point B, couple is present, and exposed movements are also marked, and this distance is x from the extreme left end of the beam and the section. Now if we apply sigma Fy equal to 0, we get minus 5 into 10 is the magnitude of the UDL acting in the downward direction, minus 10 is this force acting in the downward direction, and minus V is acting in the downward direction. And if we rearrange this, we get minus 60 kilonewton. So there is no x involved in this equation, which means that the value of shear will remain constant throughout this portion. So we do not need to calculate the value of shear separately for point C and point D. Next is the equation of moment, sigma mx equal to 0 with clockwise movement as positive. So first of all, this UDL, the magnitude of the UDL is minus 5 into 10. Now this time the entire UDL is present on the left side of the section, and the lever arm of the resultant will be from the section will be at x minus 5 with respect to the section, because the resultant will act at the center, and center is at point B, and the distance between point A and point B is 5 meters. So the distance between the resultant and the section will be equal to x minus 5. So minus 5 into 10 into x minus 5 is the movement due to this UDL. Then this 10 kilonewton force acting in the downward direction, it is also producing movement in counterclockwise direction. So minus 10 into x minus 5, the lever arm is same, and then this 20 kilonewton meter force acting in clockwise direction is a movement, and minus m, this is the exposed movement, and that's equal to 0. If we solve this equation and we rearrange it, we get m is equal to minus 60x plus 320. And if we plug in the values of x for point C and point D, we get mc equal to minus 280 kilonewton meter and md equal to minus 880 kilonewton meter. Now we need to note a couple of things about these movements. One thing is that md, how much is md? Md is minus 880 kilonewton meter. If you look at this this beam at support D, we have a movement, we have a fixed support, and there is a movement, and that's equal to 880 kilonewton meter. So the magnitude of the movement at point D should be equal to the magnitude of the reaction. And another thing, at point B we have a point movement. So for point B, we should have two different values of movement from AB side and from BC side. We should also verify that. So for portion AB, MB is minus 62.5, and for portion CD, sorry, for portion BC, MB is equal to minus 42.5 kilonewton meter. So we have two different values of bending moment at point B, because there is a point movement acting at point B, and you can see that the difference between these two values is 42.5 and 62.5 is equal to the applied moment at that point, which is 20 kilonewton meter. Now once we have calculated all these moments and shears for all the points of beam, last step is to draw shear force diagram and bending moment diagram. If we look at this beam, here is the beam with all the applied loads and dimensions. I have marked the reactions as well. So plotting of shear force and bending moment diagrams is merely plotting of the values that we have already calculated. So from at point A, the shear is equal to 0. At point B, shear value VB is 25, next value of VB is 35, and next value of shear at C is 60. Now if you look at the equations of shear force for portion AB, it will be 0 degree first degree equation for this part. That's why I've joined it with a straight line. Similarly, first degree equation for this part and a 0 degree equation for this part. This line is actually exactly horizontal. It's not drawn exactly like precisely, that's why it's looking a bit inclined, but actually it's a horizontal line. The value is 60 here and 60 here, and we have at the support we have 60 kilonewton reaction. So finally that reaction will close the shear force diagram. Similarly, we'll draw a bending moment diagram just by plotting all the ordinates, and the slope of bending moment diagram will be decided on the basis of the magnitude of shear force diagram. This is as the magnitude is increasing, so the slope of shear bending moment diagram should also be increasing. One thing is missing here. I forgot to write down the degree of the equation. You must always write down the degree. So this is a second degree line. Similarly, this is a second degree line, and this is a straight line. So this is bending moment diagram. The entire bending moment diagram is negative. So the elastic curve, because this diagram was quite complicated, so I have drawn it here. This is the beam, and the entire bending moment diagram is hogging. The beam is hogging down. So this completes the solution of this problem. So I think with this we can stop recording here. Thank you very much.